Last time I was talking about linearization of nonlinear systems, and before that I talked about state space presentation of dynamic systems. I told you that state space presentation is just a way of studying dynamic systems, right? And before that we saw that one way to study linear dynamic systems is to study them in S domain. And to do that, we take the Laplace transformation of the differential equation, and from there we obtain transfer functions. Transfer functions are in that form. Or we can use the state space representation, and in state space representation we stay in the time domain. There is no Laplace transformation involved. And if our system is linear, then for an nth order system we have a model that looks like this, a linear first order vector differential equation in this form du, and then y is equal to cx plus du. So one important property of state space representation is that the choice of state variables is not unique. So you can have different state vectors defined for the same system. And for every different state definition you choose, you end up with different matrices. Okay, so A, B, C, D matrices will be different for different state vector definitions. But obviously there are some connections, right? So this represents this system, and then this also represents this system, and hence if you are careful about what you're doing, then you get the same information from both systems. For example, if you apply an input and if you want to calculate the output you calculate from here should be exactly the same output you calculate using this mathematical model for linear systems. Okay, so here, if the system is nth order, the transfer function has an nth order denominator, which means there are n poles for that system, right? So we talked about these poles before. So these poles are related to this matrix here, and this is explained in the lecture notes. I told you that I was not going to cover this part, so hence I skipped this part, but this part of is information, so you can find the proof here of okay, so this is the critical part. The eigenvalues of the A matrix are the poles of the transfer function. Okay, so you should know this information, and if you wonder why this is the case, you can go back to the lecture notes and follow the proof from the beginning. Okay, so let me just make a summary here. Okay, suppose that I have a linear and time invariant system. From here I obtain a transfer function g of s. This is unique, and I may have various state space models. So let me call this state space model 1. And then there may be a different state space model. Let me call this 2. And this second state space model will have different matrices. So I should make these. So this is the second set of matrices, A2, B2, C2, and D2. A linear system has one transfer function, and that has n poles in state space, we can represent that system using many different state definitions. Each state definition will give us different A, B, C, and D matrices. And eigenvalues of the A matrix are equal to the poles of G of S. And these are which are unique. So that means all different A matrices we get by defining states differently should all have the same eigenvalues. Okay, so and these are pretty important. So these poles or eigenvalues, and they tell everything about the system to us. So we actually solved this before while calculating the free response or forced responses of various systems. We saw that what we do is we first calculate the poles, right? And then based on the poles we perform partial fraction expansion. And then from the partial fraction expansion we can calculate the response pretty easily. So at that point we saw that calculating poles has a direct effect on the response, because those poles become the response later on when we take the inverse Laplace transformation. And now I'm telling you that in state space the concept of the poles are still there, and it turns out that the poles are the n poles of that transfer function become the n eigenvalues of these A matrix. So the poles are a very important property of linear time invariant systems, and now I would like to show you how important they are. Okay, I guess before that there were some examples on linearization, so maybe we can very quickly go over those examples. So this is already in the lecture notes. I guess we did this one before, the pendulum example, right? So this is a nonlinear system because of this sign term in the differential equation of the system. So we can define we can write the state space form for this example by choosing two state variables, since we have a second order system, and these state variables can be chosen as theta and theta dot. When you do that, your state equations become the following. The first state equation is this. There shouldn't be dot here. There should be dot here. X1 dot is equal to x2. And x2 dot is equal to this function, and you have this nonlinearity. So the state space form is a nonlinear function. So for linearization, we need to find out these matrices, A and B matrices, by performing these differentiations. So if you take derivatives, the solution is given here. So let me not spend too much time on this. But let me tell you something to think about. This is our example. Solution for x1 is equal to theta and x2 is equal to theta dot is in the PDF file. Okay, so solve the problem yourself with choosing the state variables as follows: x1 is equal to y, or let me call it h, and x2 is equal to h dot, where h is this thing. H is the horizontal distance of the ball with respect to the vertical axis. So that means what? L times sine theta, right? Write state equations. X1 dot. Write nonlinear state equations. And linearize them. Okay, so this is going to be a very good exercise. So there is another example. This is a more complicated nonlinear system. It is this magnetic suspension system. So this is a diagram of that system. So there is an electrical circuit. A potential is applied to this circuit, which causes a current to flow through these coils. And the current flowing these coils creates a magnetic field. And this magnetic field creates a magnetic force on this ball here. Okay, so this force can be used to counter the weight of the ball so that we can keep the ball floating in the air. So this is the problem. In fact, we have this experiment set up in our controls lab. So if we can make this work, I would like to show this to you next week. So we have an experiment set up for this. We can apply a voltage and we can in fact see the ball floating here. So this is a very nonlinear system. So the equations are given in this PDF file. So there's a electrical circuit, and in the circuit there's an inductance due to these coils. So that creates a dynamic element. So we have this first order differential equation for the electrical part, and then for the motion of the ball we write a second order differential equation. So it's a 1 degree of freedom motion. It can only go up and down. So that gives a second order differential equation, and combined with this, this system has a total of 3 states. So we need to define 3 states to represent this system. So we have this highly nonlinear equation for the motion of the ball. So this is the weight of the ball, but the force created by the magnetic field is given by this relation. I squared divided by y squared. So this is nonlinear because there is this square function, and also we have this in the denominator, right? We're dividing I squared by y squared, and then I and y appear together in the same term. So all of these things are reason for this system to be nonlinear. So by choosing these state variables, we can write the state equations as you see here. This is the first state equation, which is nonlinear. x1 and x2 multiplied together, x2 and inputs multiplied together. The second state equation is linear, but the third state equation is nonlinear as well. So to linearize this system, we need to choose an equilibrium point. So for equilibrium point means the ball is floating at some fixed distance, right? So for something like that to happen, we need to apply a voltage. So without applying a voltage, we cannot keep the ball floating in the air. So to find the equilibrium point, we say that there needs to be a non-zero voltage applied. So we call it V0. Let's say V0 is the amount of the voltage applied. And the equilibrium point around that is given by this, the position of the ball, or this is the current, the current, the steady state value of the current is this much, and the position of the ball is this. So the ball will be floating at this point. And then if you find the A and B matrices, you will get these at this particular equilibrium point. And then this is an example of linearization of a nonlinear system. So if you apply a different steady voltage, if the value of U0 is different, then obviously the A and B matrix will be different, because we have U here, and this value will change, and according to that, the x20 will change as well, right? So that means the A and B matrices will change altogether. Okay, so as I said, we have this experiment set up, and unfortunately I never used it myself, so I don't want to promise too much to you, but in the ideal case, we will be able to see that this linear model is an approximation of the actual system. That means we are going to give some inputs to the real experiment. We will measure the position of the ball, and that measurement will be close enough to what we predict by this linear model. Okay? So obviously, this is a very simplified model, because in reality the system is not, the motion of the ball is not 1 degree of freedom. When you see the experiment, you will actually see that the ball moves in the horizontal plane as well. So we have these cylinders here, and then we have the ball. So this cylinder is controlling the magnetic field, and on the experiment you see that the ball can move in the horizontal plane as well. So obviously this model doesn't include that part, the horizontal motion. So we may not be able to see very good experiment results out of that, but we'll see. Okay, now let's come to today's topic. Today I would like to show you the importance of these poles of the system. And the poles are, so we see these poles in the state space model as well, in the form of eigenvalues this time. But nevertheless, they are the same quantities. So the poles are here somewhere, and then it doesn't matter how we define states. Even if we choose different state models, we get different matrices, but all these matrices share the same eigenvalues, and these are very important quantities about the system. Now let's start talking about that. To show you the importance of these quantities, these poles, I would like to use an example. Okay, so this is what we're going to study: response and stability of linear dynamic systems. In state space form, a linear time invariant system is given by these equations. And if we had the transfer function for the same system, and that looks something like this. So I'm going to show you the importance of these poles or these poles, but the stability is also concluded using these poles. So one of the very important information we get out of these is the stability of the system. And for stability, let's remember what we said about stability before. Before I told you, explained you the stability of equilibrium points, right? And I gave you this example. I said this is an equilibrium point, and then this is another equilibrium point, and we said the stability is defined as follows. If you take this system and release it at some initial condition, so this is an initial condition, if it goes back to the equilibrium point by itself, that means that point was stable. And in this case, it is unstable, because if we release the system from some non-zero initial condition, then it will just move away, right? It cannot find its way back to the equilibrium point. So this is unstable. This is stable. This is stable. And the equilibrium point. So here the key information is the equilibrium point, right? And how we defined the equilibrium point was the following. We said at equilibrium point, all the derivatives are zero. So first we assume that, let's say there's no external input, okay? So let's just think about the system itself without any external manipulation. So if u is equal to 0, then our state equation will be this much, x that is equal to ax. And in this case, the equilibrium point is defined as follows. X dot should be equal to 0. That means a times x0 is equal to 0, where x0 is the equilibrium value of the state vector. So the equilibrium point can be found using this equation. So A is some constant matrix. We multiply that constant matrix with this constant state vector, and the multiplication should be equal to 0. Şimdi bu çözümün nasıl olacağını biliyor musunuz? Yani burada x0 için bir çözüm nasıl bulunabilir? So this is a matrix equation, right? So it looks something like this. So this A matrix has some elements, and now we multiply it with the state vector x01, x02, x03, and this multiplication should give 0. So this 0 is a vector as well. So one solution is the trivial solution, which is x0 is equal to 0, right? So this satisfies this equality for all possible A matrices. So that's the solution. So can there be a non-zero solution? So there can be a non-zero solution only if the A matrix has a determinant of 0. So hopefully you remember this from your linear algebra course. Yani neyse, o aslında linear algebra işi birazcık eksiye burada karıştırıyor şeyi. Demek istediğim şey şu. And this is the conclusion. For linear time invariant systems, there's just one isolated equilibrium point, and that point is the only solution to that equation, x0 is equal to 0. So for linear time invariant systems, we can simply talk about the stability of the system instead of stability of the equilibrium point, because there's just one point. Yani şöyle demek istiyorum. Eğer non-linear bir sistemde şöyle bir durum olabilir. Bunların her birisi equilibrium point, right? So this is an equilibrium point, this is another equilibrium point. So these are all equilibrium points. So you have many equilibrium points for the same system. But when you linearize this system, then you approximate this system with a line, and that line cannot have those things, so right? So a line will be something like that, and for that only one isolated equilibrium point exists for all linear time invariant systems, and that point happens to be the origin of our state space. Okay? Good. So now it's a good time to give a break. So let's give a break and continue after the break.